Okay, in this section, we're going to talk about implicit differentiation. So let's compare first explicit versus implicit forms of functions. So explicit form of a function would be a function where you have y isolated on one side of the equals, like those. And then implicit would be where you have y mixed in with other variables or other functions, and there might even be more than one y in the equation. So that's something where it's implicit. And if something's written in implicit form and there's no way to isolate y by itself, you have to do what's called implicit differentiation. Okay, so let's practice differentiating with respect to x before we do implicit differentiation. Okay, so this is saying if we take the derivative with respect to x of x cubed, we know this is 3x squared by the power rule. Okay, when we're taking the derivative with respect to x of y, we know this is dy dx. Like, for instance, if we were taking the derivative of this, we always know that I would change the left side to be dy dx as a way to represent what the derivative of y is with respect to x, and then the right side would be that. So we have done that before. Okay, now what's different is, okay, if you have something like this where it's the derivative with respect to x of y cubed, this would be equal to 3y squared by the power rule. And then you have to apply the chain rule because y is a function in terms of x. So the derivative of y cubed is equal to 3y squared times dy dx. And you could think of this as, we've kind of done this before with u substitution when we learned the chain rule. Like, for instance, if you let u equal 5x plus 4 or something, when we're doing the chain rule, we would later use find u prime to be 5, right? So in this case, we just don't know what y is, so we have to apply the chain rule because y is a function in terms of x. Okay, and then I'll prove it later why that makes sense if it's not clicking. Okay, number 4, we have x times y squared that we're taking the derivative with respect to x. So we have to apply the product rule here. So this is equal to 1, because that's the derivative of x, times y squared, plus x times the derivative of y squared, which would be 2y, and then chain rule, so dy dx. Okay? Okay, so in this box I have the guidelines for implicit differentiation, which I'll run us through on these examples down below. But I want to talk about this notation dy dx and what it means. Okay, so that d, so the whole thing means the derivative of y with respect to x. Okay, so that d I highlighted stands telling us the derivative, and then right next to it, so we're finding the derivative of y, and then this d in the bottom, right, it's not a fraction, so it's not like the denominator. Stands for with respect to, and then the variable x. So it's just good to know what that notation is meaning. Again, it's not thought to be a fraction. It's just the notation for what the derivative is, right? So let's finally do implicit differentiation. So in this example, number 1, part A, you notice we have y to the 4th and y squared in here. So this is not explicit form. This is implicit. So we have to do implicit differentiation here. So we're going to take the derivative with respect to x of both sides. Okay, so we start with x cubed. So we take the derivative with respect to x of x cubed, and we know there's 3x squared. Okay, the derivative of y to the 4th would be 4y cubed by the power rule. And then chain rule, so dy dx. And then the derivative of y squared is 2y dy dx. And then the derivative of 9 is 0. So you'll notice anytime we're taking the derivative of any term that has a y, a dy dx will always come out of it. Okay? So the next step to do in implicit differentiation is to get all the terms with dy dx on one side of the equals and everything else on the other side of the equals. So in this case, we have 3x squared that we need to move over. Okay, so how do we do that? Subtract 3x squared from both sides. All right, so we're left with 4y cubed dy dx minus 2y dy dx. Okay, so at this point, you want to factor out the dy dx, right? So we do this, left with 4y cubed minus 2y. Okay, so we've got dy dx by itself factored out, and the last thing to do to isolate it is to divide by whatever is attached to it. So we'll have negative 3x squared divided by 4y cubed minus 2y. And so this is the derivative of y with respect to x. So you'll notice this is the first time we've ever had another variable besides x involved. So we have x's and y's all involved in the derivative, which is totally fine. And so if we want to evaluate the derivative at a certain point, we would just need to have the ordered pair of the point in order to find the derivative or find the equation of the tangent line, which we'll do an example of that later. Okay. Okay, so part B, same thing. We're going to take the derivative with respect to x of both sides. So we need to do the product rule here on this first term. So we'll have 2xy plus x squared, and then the derivative of y is dy dx. All right? All right, the derivative of 3x is 3, and then the derivative of 25 is 0. All right, so we want to move everything that's does not have a dy dx to the other side. Okay? So that's the only term that's going to stay on the left side. So we're going to subtract over the 2xy and the 3. And then the last thing to do is to divide by the x squared. Okay, so that is our derivative. All right, on this example, we're going to find dy dx of the equation of the unit circle. All right, so we're going to take the derivative of both sides, and so that'll be 2x plus 2y, and then dy dx, since we're taking the derivative of, any term with y, we'll always have dy dx. And then the derivative of 1 is 0. All right, so let's move everything to the other side. That's not dy dx involved. And that'd be 2x, so we want to subtract 2x over. All right. And then you want to divide by 2y to get dy dx by itself. All right. And so what happens here? Okay, the 2's cancel. So dy dx, our derivative, equals negative x over y. And you can put that negative in front of the fraction if you wanted to, or move it down below to the y, whatever. Where the negative is located is not important. Okay, so on part B, we're going to evaluate a couple of points using this derivative. Okay, so notice I have the graph of the unit circle off to the right. So there's two places on the unit circle where you have an x coordinate of 1/2. And so you got this tangent line happening there at that place and that tangent line happening there. So we're trying to find the slopes of those tangent lines with the derivative. Okay, so let's start. Okay, so we want to evaluate the derivative at 1/2 comma root 3 over 2. Okay, so what I just wrote, that's how you always write an evaluation of a derivative if you're using dy dx. So you draw that vertical bar right next to dy dx, and then you put a subscript of whatever the point is. Okay, all right, so we're plugging in to negative x over y, right? Because that's our derivative. Okay, so what do we got? We got negative 1/2 over root 3 over 2. All right, so we multiply the numerator by the reciprocal of the denominator, right? That's how we divide fractions. All right, the 2's cancel, and we're left with negative 1 over root 3. Okay, and then no need to rationalize it. So that's the slope of that tangent line. All right, how about the other tangent line? Okay, so dy dx evaluated at 1/2 comma negative root 3 over 2, right? That would just be the exact same process, right? Just you'd have a negative over negative, so just make it 1 over root 3 instead. All right, so you can see that has a positive slope, right? And the other line had negative slope, so negative 1 over 3. So at least we know the negative and positives make sense in terms of the picture. Okay, let's keep practicing finding derivatives with implicit differentiation. Okay, so let's find dy dx here. So we'll take the derivative of both sides. So that'd be 10x. And then we got to apply the power rule on this x y squared. All right, so that'd be 1 times y squared plus x times 2y dy dx. And then the derivative of 9 is 0. Okay. Okay, we can drop the parentheses, or the brackets. I'm gonna move that 2 to the front, just because I like coefficients up front. Okay. All right. Move everything to the other side, right? That does not have a dy dx on it. All right. So 2x dy dx will stay on the left side, and then we'll subtract 10x over and add y squared over. All right, so last thing, divide by the 2xy. So we got negative 10x plus y squared all over 2xy. Okay. All right, let's look at number 4. Okay, number 4, we're going to take the derivative of both sides with respect to x. So the derivative of tangent of 3y would be secant squared of 3y, and then chain rule, right, because 3y is inside tangent, so times 3 dy dx, right, because anytime we have a y and we're taking the derivative of it, dy dx has to be there. Okay, the derivative of minus 9x is minus 9, and then the derivative of 5 is 0. Okay, so let's add 9 to both sides. Okay. So I'd move that 3 up to the front also, because again, I just like coefficients up front. Okay, then we're going to divide by everything attached to dy dx. So we'll have 9 over 3 secant squared of 3y. All right, what can we do here? Okay, 9 and 3 can be simplified to just 3. And then we can make this not a fraction anymore, because we know the reciprocal of secant is cosine. So we can say dy dx equals 3 cosine squared of 3y. And that's a good answer. All right, on number 5, okay, same thing. We're taking the derivative of everything. So we got to use the chain rule here. So the derivative of e to the xy will just be e to the xy, chain rule, so times the derivative of xy. So we have to use the product rule here. All right, so derivative of x is 1 times y plus x times the derivative of y is dy dx. Okay, so that was a little bit of chain rule and product rule, just finding the derivative of e to the xy. All right, so moving on, find the derivative of x squared. That's 2x. The derivative of y squared would be, 2y dy dx. And then the derivative of 10 is 0. All right. All right, I'm going to drop these parentheses, so we're going to, distribute. All right, and then we can move everything that's not dy dx to the other side. So what I have underlined, we're going to move over. All right, so those are the two terms that had dy dx. So they're going to stay on the left side. All right, and then we'll have minus 2x minus y e to the xy. All right, and then we'll factor out the dy dx. It's just on the left side. Okay, and then last thing, just divide by the expression attached to dy dx. All right. All right, that is the derivative. All right, here on number 6, we're going to use implicit differentiation first, and then we're going to, on part B, write the function in explicit form and show that the derivative is the exact same, whether or not you do it in implicit or explicit. So that this is a good example. Okay, so we'll first just start by taking the derivative of both sides with respect to x here. All right. So what do we got? We got negative 2 plus 3y squared dy dx and then equals 0. All right, so we add 2 to both sides. Okay, and then divide by 3y squared. Okay, so there we go. We got the derivative with implicit differentiation method. Okay, so now we're going to rewrite the equation in explicit form. Okay, so I'm just going to rewrite what we have. Okay, so at the beginning we have negative 2x plus y cubed equals 5. Okay, so we add 2x to both sides because we're trying to get it into explicit form where y is isolated. Okay, so we can take the cube root of both sides here, or we could raise both sides to the 1/3. I'll just raise both sides to the 1/3. All right, no need for plus or minus since it's an odd root. Okay, now we're going to take the derivative, right, as we usually would since y is isolated. Okay, so the derivative, dy dx, would equal 1/3 times 2x plus 5, right, to the negative 2/3, and then chain rule times 2. Okay, so what do we got? We got dy dx equals 2/3 times 2x plus 5 to the negative 2/3. Okay, and I want to show that these two are the exact same. So what we notice here is that this is in terms of y when we did implicit differentiation. So I'm going to substitute in that expression, right, for which y equals right here. So what does that get us? That gets us 2/3, right, and then cube root of that expression squared, 2x plus 5 to the second power. Okay, so you'll notice that these are the exact same. So just trying to show that, we're not just doing magic here with implicit differentiation. It ends up getting you the same thing as you normally would. Okay, so let's move on. Okay, let's try 7. So we want to take the derivative of both sides. So the derivative of 4x cubed is 12x squared. Okay, the derivative of natural log of y. Before we do that, let's rewrite this where the 2 is up front. So I'm going to put the 2 there and just get rid of that exponent. Okay. Okay, so what is that derivative? So it'd be plus 2, right, times 1 over y dy dx. All right. Okay, the derivative of 2y is 2 dy dx. And then the derivative of 2x is 2. Okay. You'll notice there's 2's everywhere. So we could just divide everything by 2, so we could simplify right now. So I think we'll do that. We'll just divide everything by 2. Okay, then we'll move it, the 6x squared over. Okay, factor out the dy dx. All right, and then we'll divide by whatever is attached to dy dx. Okay, so y'all know we don't like fractions within fractions, right? We don't like complex fractions. So how can we get rid of that 1 over y? Well, we can multiply the top and bottom by y over y. Okay, so what does that get us? So y minus 6x squared y over 1 plus y. And that's a good answer. You could factor out a y out of the numerator if you wanted to. All right, here we want to find the slope of the tangent line to this graph at 2, 2. Okay, so we want to find this, the slope of this tangent line. All right, so, all right, let's take the derivative. So we're going to need to do the product rule here. Okay, so what's the derivative of 4 minus x? Negative 1, right? And then times y squared. And then plus 4 minus x, right, times the derivative of y squared, which is 2y, dy dx. Okay, so we just use the product rule on the left side. Okay, and then the derivative of x cubed is 3x squared. Okay, so let's add y squared to both sides. All right, and then we will divide by whatever is attached to dy dx. So that's the 4 minus x 2y. Okay, so we have the derivative. Now we want to evaluate it at 2, 2. Okay, so what does that get us? 3 times 2 squared plus 2 squared over 4 minus 2, and 2 times 2. Okay, so what is that? 12 plus 4 over 8, which is 2. Okay, here we want to find an equation of the tangent line of this circle at the point 3, 4. So we can tell it's going to have some kind of negative slope. So we'll first start by taking the derivative of both sides. So the derivative of that is 2x plus 1. And the derivative of that is 2y minus 2. Chain rule times dy dx. And the derivative of 20 is 0. Okay, so what can we do here? You know, we can divide a 2 out of everything. And we can, I don't want to do, yeah, we'll just divide everything by 2. And then we'll subtract the x plus 1 over. Okay, and let's see, divide by y minus 2. Okay, and now we can evaluate the derivative at the point 3, 4. Okay, so the slope of that tangent line is negative 2. So the equation would be y minus 4 equals negative 2 times x minus 3. Okay. And so on number 10, I want to prove why the derivative of the natural log of x equals 1 over x. And so what we're going to do first is we're going to rewrite this equation into exponential form. So the base of natural log is e, right? So e to the y equals x, okay? Okay, so what are we going to do next? We're going to take the derivative of both sides. So we're going to take the derivative with respect to x of e to the y, and then take the derivative with respect to x of x. Okay, so what's the derivative of e to the y? So that would be e to the y times dy dx, right? And the derivative of x is 1. All right, so isolate dy dx by dividing by e to the y. So we get 1 over e to the y. All right, and what do we know e to the y really to be? Well, we really know it to be x. So the derivative is equal to 1 over x. Okay, there's the proof for why the derivative of natural log of x equals 1 over x. Okay, so let's practice finding the second derivative. Okay, so finding the second derivative of x squared plus y squared equals 1. Okay, so to save time, we actually already found the derivative, the first derivative, back on number 2, right? So you typically, find the first derivative, through the implicit differentiation method if necessary. So you do that first, so we did that, and then you would take the derivative with respect to x again, right, of dy dx, and then we want to take it on the right side as well. We'll move that negative to the numerator. All right, so what do we get? Okay, so the notation we have, okay, so the second derivative of y with respect to x twice. So how do we take the derivative of negative x over y? Well, that is the quotient rule, right? So low d high minus high d low. So that's dy dx over low squared. All right. And what do we know dy dx really to be? We know that to be negative x over y. So we're going to replace that on the next line. Okay, so okay, so this is the second derivative. We just want to clean it up a little bit. So how can we get rid of that, fraction within a fraction? Well, we can multiply the top and bottom by y. Okay, so what does that get us? So negative y squared minus x squared over y cubed. So that's how you find the second derivative.